Hello, everyone. Welcome. We're going to start in about a couple of minutes. We're letting some people in as people are joining us from all over the place. So we're going to give about a few minutes before we get started. And if you want to let us know where you're joining us, please feel free to put it in the chat. You don't have to put your name, but it would be nice to see where you're joining us. I know most of the people are joining us from all around the place, so it would be nice to see where you're hailing from. You guys can see my slides, right?
Yep.
Thank you. We'll give for about a couple of more minutes to give a good quorum, and we'll get the ball rolling. We got about 10 people on. Okay, we're going to get started. My name is Jules Damji. Welcome, really, to the Bay Area monthly meetup. This is all about community. This is all about having monthly meetups so we can actually share the knowledge. You guys are an important part of the community, so we really want to share how our users using Ray and how Ray team is actually building some of the new features since we announced 2.1 and 2.0. So welcome to our monthly meetup. And again, just some logistics before we actually get started. All your mics are actually muted, unfortunately, so we can't hear you, nor can we see you. So I would advise you that if you're actually having any Zoom difficulties, please do put it in the chat. So I'll try to attend to that. And please enter all your questions that you actually have throughout the meetup in the Q&A section, not in the chat section, because sometimes it's very difficult for me to track down. So put your Q&A questions in the Q&A sections, and we'll try to answer those questions towards the end. And then are there any Ray-related questions? I'll try to answer it asynchronously, but we'll try to keep the Q&A sections towards the end of the particular talk. Here's the agenda for today. I obviously have some announcements that I'm going to be sharing with you, some upcoming events which are happening with respect to Ray. And then we have two really good talks. One is, it's one thing really to write distributed applications, which has been the goal and the vision of both Ray at any scale as well, to make sure that everybody out there who can actually write these distributed applications, the way they would like their Python code. But it's a whole different ball game, really. It's a whole different paradigm to figure out how to actually debug the thing, how to monitor those things. What are some of the lenses that you actually look through? What are the ways you can actually somehow get to the root of the problems? And we have two software engineers from the Ray team, Sang-Bin and Ricky, who are going to share us what they have been working on in terms of the observability and the debuggability of Ray applications. So they're going to share that with us from the Ray team. Then we'll have the Q&A sections. And I'm delighted really to welcome Frank and Philip from Zilis, who are going to share us how they're actually using Ray to use the open source distributed vector database that actually have called Milvus. And Philip is both an engineer as well as a contributor to both these open source projects. So he's going to share us how they're actually using the underlying engine with Ray at scale. And then we'll get into Q&A. So a couple of upcoming events. I'm really, really super excited to welcome those of you who are interested in this Ray Saturday. We are going to be hosting Ray Saturday, December the 10th. Unfortunately, it's at the time when the quarterfinals are the World Cup, so we'll be competing with that. But essentially, it's a whole day training event, starting from 9:30 all the way to 5. First in-person event at headquarters. Please go ahead and fill up that particular form if you actually want to register. It's one of our first training event that we actually want to share. We have built up a lot of modules that we actually want to share with people who are either new to Ray, who are ML practitioners, and they want to see how they can actually use to scale. So this is free. First in-house event that we actually, community event they're actually doing. So I'm super excited to do this along with my training, along with our training team. So feel free to look at that particular URL and register yourself. The slots are limited. We only have about 35 slots, so whoever actually comes first gets the spot. Another exciting thing, which is really I'm super excited. We actually had a very good race on the success of that. We're actually planning another Ray Summit in a few months. We'll have the next one in September next year at Marriott. But the CFP, the call for proposals, are opening up on 3rd of January. I think there's a date missing. 3rd of January next year is going to be open until about 17th. So those of you who are interested to share with your journey about how they're actually using Ray, please make sure you keep those dates in mind. Frank, I'll be reaching out to you and Philip as well. So keep those 2 dates in mind. So stay tuned for the website for the CRE. As I say, this is all about community. Community is really a center and the center of success of how Ray actually goes out. So if you actually want to join the community, come and join us. Go to this particular URL, join our Slack channel, follow us on Twitter, subscribe to our newsletter. You know, we have committers on both GitHub who are answering your issues, as well as on forum and Slack. And given that this is an important part of our code of conduct, I'm not expecting you to read all that, but I'm just going to live here for about 30 seconds so you can actually take a look at it, that we are strictly about code of conduct, and we make sure that this is a safe environment for all of us, both participants as well as presenters. So I'll keep that here for about 30 seconds, and then I'll stop sharing my slides, and we'll have...
Okay, should I share my screen?
Let me start sharing my screen. There we go. How does that look?
Yeah, I can see it. Brilliant.
Awesome. Okay, then I'll just get started then. So hi, everyone. I'm here to just present about the one step to distributed embedding vectors generation with Ray. So I'll start a little bit about myself. So my name is Philip Haltmeyer. I'm a software engineer here at Zillas, and I've been with this team for roughly 2 years now, and I've worked on both our Milvus and Toei projects, which I'll explain in a few seconds. And those are my contact links if you ever want to connect with me. So what this presentation is going to be about is mainly our vector database system and our pipeline solution that fits in its ecosystem, and how we incorporated Ray to kind of distribute our system in a one quick, easy step to get the whole thing working. So yeah, let's first start about the background of our vector database. This is where everything sort of stems from. It was the first idea we had and our first step into our ecosystem. And to kind of go over this, you first need to know what vector embeddings are and what we're trying to deal with. A lot of you guys might be, guys and gals might be engineers. You might have a good idea of how unstructured data processing works, but I'll do a quick run through of what's going on and why it's difficult to solve. So let's begin with what unstructured data is. Data can usually be divided into 3 categories, usually being structured, semi-structured, and unstructured data. Structured data is stuff that can be pretty much stored in a relational database. Data with defined patterns and values, which are easily grouped together. The easiest way to think of this is things that can be stored in Excel, strings, numbers, states, things that computers can easily process. Semi-structured data is something that's a little bit more confusing. It's not a term used too much, but it still exists. And this is data that is consistent to some sort of characteristics, but doesn't conform to a rigid structure. So the best idea for this are JSONs. JSONs have consistent kind of syntax for them, but their structure isn't always the same. So when reading JSONs, you pretty much can't hard code how you're going to read it, because they're varying data values and every JSON can be different. And lastly is unstructured data. And unstructured data roughly accounts for 80% of all data that we have today. With this data, there is no structure within and no structures that computers can easily understand. So for this, think of images, videos, audio, anything like this. And this is the one that we're trying to deal with. So why is it hard to deal with? When we look at structured data, it's pretty easy to deal with because it has defined patterns and values and can be grouped together pretty easily. As we said before, this is perfect for relational databases. And that's pretty much the main solution that's used for those. Unstructured data, on the other hand, hasn't really had any analytical methods to kind of deal with this data, and up until now. So now in the past, I would say five-ish years, everyone knows about neural nets, and those have been blowing up. And this is now a route that we can deal with this unstructured data. Before we had nothing, but now we have these neural nets that can kind of understand the data that we have. It gives our computers a way to process this data and kind of make use of it and kind of make it comparable to other things. So with these neural nets, we can throw our unstructured data through, and we can extract vectors. With these vectors, unstructured data that goes through, if it's images with the vectors that are resultant, two images that are roughly the same in our view will most likely have vectors that are very close together. So images of two cats will most likely have vectors that aren't too far away from each other. Let's say if we have an image of a cat and an image of a monkey, those will be more distant. And this is how we can start comparing our data and processing our data. And the ultimate problem now has become vector computation. So why is vector computation difficult? So once we have these vectors, you might think, okay, we can store these in relational database, or we can do something like that. Well, the difficulty comes in the form of how we compare these data. For example, when we compare to regular numbers, and the issue comes in is that regular numbers, you have your arithmetic operations. They're pretty easy. You can do these comparisons, and you can work on your data with predefined set patterns and quick and easy executable, pretty much, operations. With numbers as well, if you're going to compare them together, you have the simple comparisons, less than, greater than, equal to. And these are pretty well defined, and they're easy to calculate, and they're easy for computers to process. And then when trying to index these numbers, you have pretty good methods of doing it because they can be easily compared. And a simple example of this is B-trees. Vectors, on the other hand, can't be compared that easily this way, because the only way that we can kind of compare between them is through similarity metrics. And the issue with this is similarity calculations are pretty difficult. As you can see the equation, they are not the easiest to compute, and they're normally much slower than arithmetic comparisons and number comparisons. And because of this, we can't have exact greater than or less thans. If we have two vectors, some indices of that vector might be greater, some might be less than, but there is no, this one is a bigger vector, this one is a smaller vector. And that's why with indexes, with the vectors, we kind of move to these approximate nearest neighbor algorithms. And here we have two algorithms shown, which are graph-based on the right and cluster-based on the left. So those aren't the only two types. There's multiple different indexing algorithms that came out with vectors and with this kind of new age of neural networks. The first one that is pretty popular are hash-based indexes. And these use hash algorithms that are a little bit different to normal hash algorithms. Instead of avoiding collisions, they want collisions between similar inputs, because this is how you're going to get your similarity. If you get collisions, that means those are most likely similar values. Next comes the tree-based route, which comes in the form of Spotify's Annoy algorithm. And Annoy builds binary trees by repeatedly splitting the data by a hyperplane, constantly splitting it to as many hyperplanes as you want. And then near the end, you perform a search by going down the tree and choosing the side of the hyperplane that the query vector falls into. This is a pretty popular one that's used, and it's used in Spotify's systems right now for, let's say, an example is your recommended music or something like that. This is all based on kind of encoding the music into vectors and then finding similar vectors in the database of their music. The next one that comes after that is Spotify's Face library, which is inverted file based. This, I would say, is one of the most popular index types, and it's probably one of the most used in a lot of systems. The way that the inverted file base works is that it's built on clustering. So with this index, you take all your values, you your vectors in, and you throw them in, and then you calculate centroids for all these values. And by building up these clusters, you then store the actual values below the centroids. So when you're performing a search, you compare your search vector to all the centroids, and you match the closest centroids and then brute force search through their inverted list. And then lastly, one of the more revolutionary ones is the HNSW, which is used the most. And this is a graph-based index, and it's a multi-layer graph where at the top you have a very sparse graph. And for each level, you go down by comparing whatever values are closest, and you go down a level. And you keep going down levels, going to the most similar routes, the closest graph nodes. And by the end, you will find a little cluster that is based on what's the closest result for your vector. So with these algorithms and indexes and with these issues, we decided that our first project would be a vector database. And this is important because a lot of these indexes don't really have a way of managing your data. While they can build up these indexes and can do all the searches on them, you can't modify them, you can't update them, you can't delete values without re-indexing all your data. And this is a big issue because with so much data coming in, you will constantly need to rebuild your index. And with our system, you're able to search, store, and query vectors at the trillion scale in mere milliseconds. And with this Milvus, our vector database, you take advantage of all those previous vector indexes. So you can choose whichever one of those you want, and you can run those. So you can test out and you can find the best results for your use case. And the system is fully cloud native and elastic. And what we noticed, so we released this a few years ago, I believe 2017, and we built up a pretty large user base. But we have one main problem that we see with a lot of our users. And this is that they really enjoy using our vector database, but they need help with the steps before generating these vectors. Sometimes with some companies that kind of use our Milvus, they don't have their own ML teams, and they don't really have the manpower to create these complex models that they need. Companies that are large usually have their own ML teams, stats teams, and all of this, and they build pretty much all these tools internally, and they don't release them to anyone. And we find that to be a problem because we want to get as many people to be able to analyze their data and use it how they want without having to build up this entire ML team. So what's the best way to help these users, and how do we fill in this hole? So this is where our pipeline solution came in. And before going over what it is, I'll go over why it's really hard and why a lot of these companies need entire teams to deal with this. So one of the first things that happens that users are having errors with is that it's very hard. And it's very complex. Data can come in many different ways, many different modalities. So images, as before, images, audio, video, medical charts, molecular structures, a lot of different data types. And let's say if you have a pipeline that's for images, it's really hard to adapt and modify for a pipeline for videos. There's a lot of mid steps that you have to do, and this requires a lot of work. Similar to this, a lot of the tools that we currently have for this lack standards. So switching between these different data types might result in a new tool that you're using, a new library, and they might not play together well. One might be stream-based, one might be batch-based, one might be streamed in a different way, and it kind of breaks. So you end up having to create a whole new solution for data that's very similar in the grand scheme of things. An image and a video, if you're only doing frame analysis, pretty similar in the steps after. So this is also how solutions there, one size doesn't fit all. Every solution will not really apply to different types of data and different inputs. And as before, as I stated, a lot of companies don't have these giant ML teams that can handle building up these tools internally. So this is where TOE comes in. TOE is our second open source project. And what it is, it's a framework for unstructured data processing. And it simplifies this pipeline creation for compute and embedding generation. So originally this project was made mainly for creating embeddings, but we also realized that it's not limited to that. With our kind of pipelining style, you can pretty much make it do whatever compute pipeline that you want and compute processing you want. So TOE fills in this space before Milvus, this space that users are having trouble generating their data and generating their embeddings. Sorry, one sec. This Zoom thing moved over my slides. Do you guys see that? I have the Zoom bar on my slides.
I can see it.
But okay. Sorry
can
about.
see it. Yeah, yeah. I mean, I can see the code. It's hard to read. It's a small font, but I can see the text and all that.
Yeah. Okay, I'll ignore it then. So what does TOEI bring? So TOEI brings a modular Pythonic API for chaining different types of operators into pipelines. And what this means is, as in the image with the code, it's a little bit small. You can chain together many different function calls to create these pipelines. And these function calls can be separated, so you can do tabular style data where you're specifying your insert and outputs and chaining those later on in the code, or you could do chain like where every input is the output to the every output is the input to the next function. And with TOEI, we provide a hub of over 700 state-of-the-art models and data processing functions. So on our hub, you can pull up all of the new computer vision models already pre-trained and able to be trained on our platform. And it also integrates various tools and libraries so that if you want to use a new library, let's say for your data input, you're using Spark, or if you need access to FFmpeg, you're able to kind of use these and kind of click them in easily without having to worry about this standardization of the inputs and outputs. So what's missing from TOEI right now, and what do we need? So currently have no means of scaling out the pipeline for our production purposes. We need to take advantage of multiple machines to speed up compute, but we don't really have the means for this. Distributing compute and optimizing execution is a project of its own, and the team for this is not capable of doing all this. There's a lot that goes behind distributing so much work and upkeeping of clusters and organizing execution where it should be sent to which machine and all of this. And we also need, since TOEI is designed as this simple tool, we want the backend for this parallel compute to be as easy to use as possible. If we end up bringing in some backend, which takes a day to learn how to even deploy it, that will kind of be against the purpose, because TOEI is designed to be easy to run and very fast to run, and you don't really need much knowledge about it to get it working. And we also hope for a backend that won't require too many changes to our framework. The reason for this one is mainly we're trying to build this up as fast as possible for our users, for a way to get them to be able to use the data. So we want to build fast and fail fast. And if we require a lot of changes, ultimately this tool will take too long to get to users, and they might move to something else, or they might abandon the project. And what this ultimately is looking like is we need a fast way to get onto the cloud, to get this pipelining solution onto the cloud. So this is where we kind of use Ray. So why did we choose Ray? We chose Ray for these main reasons. First of all, Ray is capable Ray is able to kind of distribute our heavy compute operators to the external machines with ease. This means that for these operators, and when I say operators, those are like units of work in our pipeline. Let's say calling inference on a neural net. So with these operators, we require a lot of compute. Sometimes users' machines or the local machines can't even fit a model. So we need a way to run all this online. Another thing that we really needed was the ability to keep state for certain operators. And this is where Ray Core comes in with our actors. This is very important to us because we also offer the ability to train these models, and you need to keep state if you're processing all these inputs and training your model. Otherwise, no training would occur. What Ray Core also allows is for us to keep our current design pattern. This one, as I said before, for kind of building this up fast and getting it to users, was really nice because it plugs in very quickly and easily. And most importantly, we want it to be, Ray is very developer friendly for usage and deployment, which I'll go over a little bit later. So distributing to the cluster is really easy with Ray. So because of Ray's easy deployment with the Kubernetes operator, it's very simple to get it up and running. And it's easy for our users to get up and running as well, which is most important. And then for the API, for us, it's very easy to get going with because of the simple uses of the decorators that are supplied. For pretty much any of our functions that we already had internally could be converted to array function with a lot of without any hard problems that we to face. So this simple decorator with Ray was really useful. And another big one, which at the time I know right now it's been getting upgraded and kind of improving, which is awesome, is the Ray client. So with the Ray client, for us, it was great because when developing, it would allow us to quickly test our operations on the cluster without having to constantly move files or constantly use Vim and all of these things. And it allowed us a way to test if our serialization is working, if everything's working. So this ability to remotely connect was great for us. And it's also great for our users. For them, it also allows them to quickly test if their pipeline works with Ray, if it's going to be running well, and allows them to check kind of to see what kind of speed ups they're getting. With Ray, what we're trying to do is get our most compute heavy operations kind of offloaded. When you're connecting remotely, sure, the connection might be slower and the passage of your data might be slower, but this computation is the one that really counts. And with the Ray remote client, you can kind of see, you can get a general idea of what kind of savings you're getting and what kind of compute savings you're going to get in time and space and all these things. And it lets you kind of optimize your pipeline around that. And another thing that allows you to do is quickly test out and then optimize the rest of your pipeline or the operator itself to see where you can kind of get some speed ups before you end up deploying to the head node in the Ray cluster, which deploying to the head node in the cluster for production, it's good for production, but when you're messing around, playing around, trying to get everything to work, it gets pretty difficult. So we really like this feature for that. And I think a lot of users will also enjoy the ability to connect without having to move files around and run on within the Docker container of the head. So now I'll go a little bit over, sorry if the code is small, but going over a little bit of the stuff of how we moved over to Ray Core for our parallel compute. So statefulness in our operators is required in many situations. As I said before, some operators require training where we need to keep state, but there's other operators as well. And these include metrics overall. So when you're going over your data, calculating the metrics of everything that's incoming, maybe calculating averages over the entire data or subsets of data, and things like this. So we need to be able to keep state with these operators and when they're acting on values going through the pipeline. So the best solution that we kind of came up with was to wrap our operators with actors. And for those who don't know, the Ray actors are pretty much a stateful task. It allows you to kind of use Ray like the task and task mission, but keeping state and allowing you to kind of do what we need here. So by wrapping our operators with Ray, we solved this issue of state. One issue that we did come up with was, or one issue that did come up was that that some serialization issues occur with operators since we have this hub. The hub ones are very easy to deal with because they are pretty much enclosed completely. They have their own requirements. They have their own, all the data that they need. With user-defined local operators, more issues come into play where some parts of the operator might not be serializable. The requirements for that operator are unknown. Since it's during the runtime, we don't know which requirements are being required, and serializing this kind of stuff is very difficult. So for future work, we'll probably have to put in some more effort into the serialization of our operators. But this is one little area that we had a bit of trouble with. For now, we kind of push users to only use our hub operators, so the ones that we can download and find online. Anyone can put their own operators up there as well. And with this solution, it doesn't really require any changes by the user for their pipeline. This is all done behind the scenes, which is great because there's not a lot of settings that users have to start messing around with to get this working in the distributed sense. So as I said, this whole package requirement is a little bit of an issue, even though for the hub operators, it's much easier to deal with. Being that we can now load these operators into actors, the next step is kind of determining how do we get their packages onto the machine that is running the actor. So each operator has its own requirements text file. So the simple solution that we came up with is just to kind of reuse how we do it for our Tohi pipelines. within Tohi, we have a simple system of how we're downloading. We're just we have the ability to kind of call pip and download or download libraries from wherever it's specified in the requirements or some other areas as well. And with this already pre-built, what we ended up doing was within each actor, we kind of set up a pipeline of just one operator, which allows us to let Tohi deal with all the package requirements. One other issue that we ran into was that these Tohi in general uses default cache locations. And since we can have multiple actors on the same machine, if we have these default locations, then we will run into deadlocks, and that's not good. So what we did for this is we overrode the local default locations for every actor so that they would have their own space to work with. And then everything ran really smoothly. We got many speedups and very easy to use kind of execution on this Ray backend for our parallel compute. And within keeping our current design pattern, what we used previously was thread pool executors. These were working well for parallelizing locally, even though, yes, it was thread-based. And the Python GIL for a lot of these things would kind of not allow for too much improvement. But with our actors and Ray, we could use Ray actor pools to kind of smooth out this transition to the kind of distributed execution engine. The Ray actor pools could easily fit in. They pretty much function the same way as thread pool executors, by sending values and receiving values back. And this was easy to plug in to our coroutine based system. And this was a great thing because it allowed us to speed up our development of this and get it up and running. So what the results look like is here. Hopefully people can see the code, but pretty much this is how our kind of pipeline looks like when I say chaining operators. So in these in this chain, you can see the different kind of calls that you're making, the different operators. In the brackets are their inputs and outputs, and then in the parentheses are the parameters. And with this Ray core, all you end up having to do is put a set parallel and before whichever operation you want in Ray, and unset parallel after for removing for kind of stopping the next few operations to be in Ray. And what it ends up looking is we have our pipeline down below, and all our actions are sent to the Ray actor pool, which it then pulls the operator from the hub and performs everything within the Ray actor and sends the data back to our pipeline. And ultimately, this is how we combined Ray core with Tohi and what we're kind of dealing with, and how pretty much the future is going to look for Tohi. So we did face some issues or one issue in general that I already talked about a little before. I know Ray has been updated a little bit since the last time we kind of updated the Ray version that we're using in Tohi. But the main one that we kind of had issues with was the serialization of our callables and some of our user-defined operators. The serialization had difficulties because pickle that is used by Ray can't serialize too much or can't serialize the specific use cases. We did try using DIL to kind of serialize before moving to Ray, but again, DIL also ran into some issues. So most likely what we need to do is work on custom serializers and kind of put that on our end. Hopefully maybe there is some solution for this in the future, but yeah, we'll have to see for that. And for future work, the main things that we really need to do are kind of move our system to a full async system to kind of improve speed and kind of not deal with the GIL as much. And we ultimately want to work with Ray Serve. We want to convert our pipelines to DAGs and that are compatible with Ray Serve, and then end up executing everything within Ray Serve to kind of take advantage of all the speedups that we can get there. And that is pretty much what I have to say. So if anybody has any questions.
Excellent. Let me see. I have a question from Rajiv Abraham. Serializer. I don't know if you tried the Cloud Pickle one to actually use to serialize your your operators?
I think we did. So I think we used Cloud Pickle Dill and the different versions of Pickle. And I believe there's one more, I cannot remember which one, but we used all the different types of pickles that I could find. But unfortunately, I think the issue is, yes?
Yeah, go ahead. Yeah, go ahead.
I think the issue is more down to the core of some of the things. I think the big part of it is a lot of the serialization will have to be on your own. And with some of these like Dill, it ends up pickling too much and it could slow down the system quite a bit because it will start sending these huge files between the storage or the pulse, or not pulse, or I forgot what the storage that Ray uses. But yeah, with some serializers, it kind of gets too big and then it ends up being too slow. So most likely the route forward will be custom serializers on our end.
Something actually that came up in my mind, Philip, and you were actually showing about the different kind of types of indexes that you have to deal with, all the different algorithms. There were 4 types that you actually mentioned. One of them was the one on the far right hand quadrant was the one that's more popular. Which ones are the one that you actually are using in Milvus, or you're supporting all the 4.1 to do all the similarities?
We're supporting all of them.
Okay.
We're supporting all of them and the new ones like Google Scan and a few other ones that are coming in. Yeah, there's a lot of work going on into this, and then there's combinations and quantization of these different algorithms kind of to speed them up. Unfortunately, sometimes at the loss of accuracy and recall, but there's a lot of mixing and matching between the two and kind of getting it all working out. But pretty much all of them. And there's a new one also, disk ANN, which is like disk-based. A big issues with these indexes is that they can get pretty big. So for a lot of people, like let's say you have 400 million vectors using HNSW, I think you're already going to be in the 1,000 range gigabytes of RAM needed for kind of executing these queries. So disk ANN is a good one because we're kind of throwing that all into the disk and keeping the memory usage as low as possible.
So in terms of the operators which are wrapped around the actors, right? So you have an actor which is actually sort of a wrapper around the operator, and once the query comes in, can you give an example of what a two-way operator would look like? You have an operator, but what does it do internally?
So an operator mainly internally, it's kind of a class. It's a class, pretty much exactly. It's a class, and the class has a call function and init function, and pretty much what's going on is in the init you're putting all your stateful stuff that you need kind of stored, and the call is what you're executing on, and the call has the inputs and outputs. Our engine internally kind of takes over. The inputs and outputs are kind of undefined. It's changes during runtime, and our engine deals with grabbing the correct values from the DAG pretty much to input into the operator and pulling out the data. So that's what's pretty much the engine kind of stays local to the script that's running the code, but this operator class gets sent over and we just send over the input and grab the output.
Okay. So the operator is like, if I could call it, it's like an SQL function that you're actually executing on the Milvus, and then you're getting the output back.
Yeah.
Is that fair to say? Okay. So
yeah.
You did mention, you alluded to the fact that you decided to use actors rather than tasks because actors are stateless, and I mean tasks are stateless, but actors are stateful. What sort of state are you actually maintaining in each and every actor?
So in each and every actor, a lot of the ones is with training of neural nets. So you keep your weights and your actual neural net on the state and metrics. So let's say you're logging how the accuracy recall of everything that's going on. You kind of need to keep that there to calculate the final values. There's also the big one was like, let's say you're normalizing or averaging out over your data, you're doing normalizations. You do need to kind of keep state. And being that this is kind of machine learning oriented, a lot of those operations that you're doing need to kind of keep state. There are a few where you don't need to. And I do believe we also have tasks utilized for the ones that we don't need to. Like kind of, let's say you're doing like maps of additions or subtractions or something like that, where it's not really needed, where you don't need like a full operator, you just kind of have this smaller subset. But mainly it was a lot safer to go actor based, even if some don't require state, because it was so easy to implement it, and so quick with the Ray actors to do it. And there wasn't no loss really in speed up. So
So
that's why we kind of went that route.
right, in terms of the pool of actors you're actually using, how many actors do you actually have, and do they actually each have a copy of the model, or you actually use that particular model and put it in the object store and then let it be sort of distributed across all the actors?
So for now, the amount that we choose is in set parallel. You can kind of set how many workers you want,
Okay.
and that's pretty much how many actors get replicated.
Mhm.
And for now, we are kind of using every actor has its own model.
Okay.
There is a slight move to kind of moving away from that because it ends up taking a lot of space.
Mhm.
And with training, it kind of gets difficult. But for now, we decided to kind of keep it running well and kind of get it working. But in the future, I think the move would be to kind of store in the object store and then have each one kind of grab it. But yeah.
And last question, from Rajiv, I think he noticed something in your code. I noticed your imports were within the methods. Is that a code style preference, or is it a technical necessity?
I believe it was a technical necessity in I believe I'm assuming it's this one with the from Tohi.
Yeah. Yeah.
We did it here. I believe it's necessary because this is what's going to be run on the actor and on the separate machine. So we're sending Tohi over as a package in the Ray init to kind of have the cluster have access to that package. So I was importing within the class just in case. I actually believe you do need to. I'm not sure if it's just in case for this one, but importing it there to have what we need. Because we're treating every single actor as sort of its own little Tohi pipeline. So we want to have that imported there and to have access to it. And we don't actually need these imports in the rest of the code. It's specifically within the actor.
So I'm curious to know, what version of Ray are you currently using with Tohi and with Milvus? Is it
2.0?
2.0. Okay, so you have upgraded 2.0. Have you guys looked into how Ray Air can actually help you with the other aspects of some issues that you actually faced, or it's still under investigation?
Still under investigation.
Okay.
I was just mainly looking. There were improvements with the client and all that.
Yeah.
But still under investigation for the rest.
Okay, brilliant. I think there was a final one question that somebody asked. I think it's Ed who asked, is this presentation going to be available online? And Philip, if you don't mind, just send me the PDF file and I'll just upload it into our shareware and we can share it with the audience. Is that okay?
Yep, sounds good.
Brilliant. I think with that, we can just move on then. Thanks a lot, Philip. I appreciate that. Thanks a lot for Frank joining us. And we can just move on to our next presentation. Are you guys ready?
Okay, so then let me take it over.
Okay, brilliant.
Hopefully this time it'll work.
Well, second time and third time is a charm. But I normally have it my cell phone or my iPad, because if I'm on a single machine and I can't share my speaker notes, I normally do that.
I see. Can you guys see my screen now?
Yeah, we can.
Okay, got it. I assume it's working now. Okay. Yeah, so just in case anybody came to Ray Summit last time, this talk is a pretty similar talk. I think the first part will be the same, but later part, since the Ray Summit in August, we made a huge improvement to the observability and dashboard in general. So in the later part, we're going to more focus on the new features we developed for Ray 2.1 and 2.2. So I just let everybody know about it. Yeah, so let me start. So I'm Sang-bin. I'm a software engineer at Anyscale, and I'm gonna have a presentation with Ricky, who's also a software engineer at Anyscale. So let me have a brief introduction of ourselves. We are both software engineers at Anyscale. We are working at the Ray Core team, also have been developing a lot of features in Ray Core, like Ray Core distributed systems. And currently, we have a huge focus on improving the observability in Ray because this is something a lot of users actually complain and have a hard time when they're using Ray. And also we are from Anyscale. Just in case people don't know Anyscale, it is a creator of Ray, and we are building the scalable compute for AI and Python. And if you're interested in how to debug Ray applications, and if what tools are available for debugging, and also what's new observability features in recent Ray releases, including 2.0, 2.1, or the 2.2, which is gonna release in a few weeks, then this is the talk you're looking for. Let me start from the outline. So we're gonna start from the requirements in Ray observability and what kind of tools we had before 2.0 and the new feature at 2.0. And also we're gonna have a demo that actually includes features for 2.1 and 2.2. And we're gonna finish the presentation with the feature roadmap. So let's start from the first section. Ray provides the APIs to build distributed applications, and this hides the implementation detail of distributed systems and help users to focus on building applications running at scale. But how does it look in the real world? Firstly, you're going to have a head node when you actually run the Ray, and you're going to have a lot of worker nodes. And actually, in the real world, when you have large scale workload, you're going to have like hundreds of nodes. And this is the actual benchmark we've done very actively in the nightly. So we can have like hundreds of nodes, tens of thousands of actors and tasks, and we can even have millions of objects in the object store. And these are all running and stored concurrently across the cluster. Then with all this in mind, what if anything's going wrong? So for example, you imagine just one vector failed or some manual vector failed, and debugging this is not trivial because there are a lot of information, a lot of data, and you need to actually like get into the machine, figure out why each vector failed. Without the help from the systems, this kind of debugging is way more difficult. Then how can we still make debugging easy in Ray with this environment? I think there are two main things we need to focus. The first thing is we should understand the workflow when people are debugging, and we should provide the tools that help people following the workflow. So just let me just quickly go through the workflow. So when you actually debug any problems, if your application fails, the most important thing is to have the visibility into your applications. The monitoring is very important. Like what kind of things are actually happening in the from the cluster and application. And then if anything goes wrong, the problem has to be surfaced to users very clearly. And then when there's an error, then there must be proper tools and data that help users to figure out how to fix the issue. And then of course, you need to have some mitigation strategy based on these tools and error messages. To support such workflow, there must be corresponding tools for each step. Like for example, when you monitor your applications, you can have dashboard or logs or some sort of like built-in progress report from the system. When you want to surface the error, the system should have a clear exception model as well as the good error message that explains all sort of failures happening in the cluster. And when actually things go wrong, you should be able to debug using tools like debugger or profiler. And systems like Ray, we need a debugger and profiler that should work at scale or that should work in distributed systems. So let's see what sort of tools are available before Ray 2.0. What kind of observability was available. So we're going to start from the case studies. So usually there are two typical failures when you use Ray. The first thing is the application failures, usually failures from user code. And there are, of course, system failures, like your application hangs, some configuration has issues, there's out of memory and things like that. Previously, before Ray 2.0, the first case was well supported, and I'm gonna go through features that help debugging application failures. So this is a simple toy array application. As you can see, it creates the 4 vectors, and you call into all of vectors using print task method, and then you get the reference. And this is how it looks. You're going to have 4 different vectors. And then when you do the local development, usually the easiest way to do the monitoring is to add a log. So usually what people want is to add a log like this. You just want to print something, and you want to actually see this log from your script or from whatever method you have. And this is fortunately very well supported in Ray. So by default, all of the logs from test connectors are printed to the Ray driver program, which is just Python script that runs all of the code. For example, imagine this kind of function. You just have a print statement within your task, and in your main script, you're able to see actual log messages with the clean metadata. And then Ray also has a Ray log API to actually help you to access logs of actor, task, workers, and other system logs. So this is a simple example. So as you can see, you're able to access log through the Ray log API. You specify the PID, which is equivalent to this task, and then you're able to see the log messages from there. And then now imagine you have the error nose code, like this code. For example, let's say your method now has a division by 0 error. In this case, the error has to be surfaced to users so that whenever anything goes wrong, you can actually see what goes wrong and start debugging immediately. And then this is also pretty well supported in Ray. So all the primitives in Ray, like task, object, actor, generates the object reference like this. And then if anything goes wrong with the generator of the object reference, so in this case, the print task, which has a division by 0 error, then the references are going to contain the exceptions. And when you actually call ray.get, the exception is going to be propagated back to users. This is a pretty similar like exception model from other asynchronous programming. And then this is the actual error message. So error message is going to show you the metadata of your task that actually has an exception. So in this case, the PID, what's the IP, as well as the exact error messages. And also, whenever there's any sort of system failures, we also figure out exactly what kind of what was the root cause of the failure and send the exception back to the user with the correct metadata like this. So this is a typical error when you have the out of memory error, because the operating system sends a sleep kill to the worker and the worker is unexpectedly killed. And this kind of messages are reported back to the users. So once you know what the error is, the next thing usually people need is to debugging. And when you debug Python program, the typical workflow is to use a debugger. For example, like this, you can just simply add a breakpoint, and you want to run the debugger like PDB or the VS Code debugger or whatever debugger you like. So Ray has its own distributed debugger to support this case. So when developing Ray, many users want to use familiar debugger such as PDB. And Ray currently has the PDB integration to support the distributed debugging. Unfortunately, PDB is the only debugger we support. But it's going to look like this. So you can just add a breakpoint into your task or actors, and then you just call the CLI command Ray debug, and this is going to actually bring you to this output, which shows you all of the task that's running that has the breakpoint, which line the breakpoint is, and you're actually able to jump into each index and use PDB to debug the issues with the debugger. The last thing is, let's say your application is slower than you expected. For example, let's imagine your actor is doing some busy work and returning a big object, and you figured out one of your actors is actually slow. You wanna know exactly why this actor is slower than other actors. Then how would you figure out? So sometimes users want to trace this low-level per worker operation to find the exact bottlenecks in performance. And Ray supports the timeline API to allow users to do this. So for example, as you can see from the right screen, you can see individual worker and you can see what individual worker is actually running. So in this case, the worker is actually running the task for 85 milliseconds, and you can see most of the time was spent on storing the outputs, meaning probably the output of this actor was really large and it takes really long time to storing the output. Maybe there was spilling happening or some other issues related to the size of the object. The last thing I'd like to introduce is the visualization. So Ray has a native integration to metrics, Prometheus metrics, and you can easily export metrics and visualize through the Grafana. And also Ray has a built-in dashboard package with the Ray, so you can actually see the cluster state, what kind of things are happening in the cluster easily in a glance, and diagnose any problems happening. And this is actually the part that we made a huge improvement in Ray 2.0 and 2.2, and we're going to have more detailed demo in the later part of this presentation. Okay, so I'm gonna pass the slide to Ricky. Can you take it over, Ricky?
Yep. Could you stop sharing? Okay, cool. Awesome. Thanks. All right, cool. Thanks, San. Could you all see my screen?
Yes, we can.
Okay, cool. So I'm gonna talk about what's new in Ray 2.0. So really in Ray 2.0, there are two things that we focused on. One is we introduced something called State API, which allows people to query high-level Ray states, things like actor, task, and just having better Ray exceptions. So I will actually focus more on the Ray State API today. So the State API is really a bunch of APIs that's both available in CLIs and also in Python SDKs, where you could get high-level information of the tasks, actors in your cluster, or drilling down into more details of individual task, object, or actor. So let's go through each category of the APIs together. So the first group of APIs is the summary API. So you could do that from the CLI by using Ray summary, right? So for now, there are three different categories that we currently support, the tasks, the actors, and objects. So for example, you could use Ray summary task and with an optional -- address for the Ray address if you are connecting to a Ray cluster remotely. So this Ray summary task will give you a summary report of the tasks that are currently running or have been running in your cluster, right? So you see there is the identifier of the function and the class name. And so this usually is the function name that in your script. And there is the state count of different tasks in different status, right? So there are ones that are running, there are ones that are finished, there's ones that are currently waiting for dependencies, or for example, for node assignment, etc. And there's also the type for different tasks. So this gives you an overview of like what different tasks are currently running or being blocked in your cluster, which is usually a pretty good first step if you are debugging something. So besides task, you could also query the summary of your actors. So similarly, the actor summary gives you a simple count of how many actors that in different states they are. So the actors are identified by the class name, the actor name, and also the number of actors in different states. So you could see actor might be pending creation, alive, or dead. And there's also the Ray summary objects, right? So Ray summary objects work similar to Ray memory. If people are familiar with that, more the legacy APIs. So you can see that I have a script which has a bunch of Ray puts and holds the references to those objects. So Ray summary objects give you an overview of like what the different objects you put into the object store. And it has things like the reference count type, whether it's a local reference, like how many they are, and the tasks that have been creating or owning the owner task that created those objects and what the states they are, and the node number, and also the approximate size of those objects. So it also gives you the call sign information to let you know where these objects are being created in your script. So these let you trace down if you have any excessive memory usage in the object store. So the Ray summary API is a bunch of APIs that are pretty good for high-level overview. So you sometimes also want to drill down into individual resources, such as like individual tasks, individual actor. So the Ray list and get supports more category of the resources. So other than object, tasks, and actors, it also allows you to query states from workers, runtime environments, placement groups, nodes, and jobs. So for example, you could do release task. So the default columns that returned by the release task include information such as the task ID, the name of the task, of course, the scheduling state, the job ID that this task is running, and the node ID associated with that task if the task has already been assigned a node, or an actor ID if it's an actor task. And the list API also supports simple query, right? So it does allow you to query with equality or or without with an activity here. So you could specify things like I want to query all the tasks which are not finished, and they are the PPO.train, some arbitrary name of those functions. So this will allow you to really drill down into a subset of tasks that you're interested in, depending on use cases. And similarly for actors, you could also do the array list actors with a feeder. So for actors, the array list returns the actor ID, the state of the actor, the job ID, similarly the name and node ID and the PID, where the PID is the process that runs the actor. So sometimes you are only interested in maybe one or two actors which are behaving abnormally. So in that case, you could get the actor ID, for example, by a dead actor using array list actors. And then you could grab the ID and then drill down into more details with array get actors. So the get actors will return information such as the death cause, right? So if this is a dead actor, why it was killed, and it also gives you information about where the actor was originally on, like the node ID and IP, the process ID as well. And you will also get information such as whether this actor is a detached actor, the array namespace that the actor runs in, which is essentially the session name, and the required resources of the actor that needs it to run, and also the serialized runtime environment or basic runtime environment, which include things like environment variables or dependencies. So once you know a certain group of resources, let's say actor, most of the time people also want to grab like the logs of those information or those states to see what exactly is happening. So the Ray State API also introduces 3 categories of logging CLIs comments or Python SDK comments: the cluster, actors, workers. So Ray logs cluster will return all the logs that are generated by Ray sessions into different categorizations. So you can see there are system logs, for example, the GCS server. There is the application log, which are the worker log out and worker log error. And you could use Ray logs a glob, basically to narrow down into a specific set of logs that you're interested in. And if your filtering requirement only returns a single log file, which is usually when you do like exact match, right? You could actually pass in the name, for example, worker, dash the worker ID, the PID, the out, which you could copy paste from the Ray from your Ray logs comment above. And then when you do a follow, this will basically follow the specific log, just like tailing. So this will be pretty easy if you want to retrieve the logs when you know a specific log file handle name. So for more details of the state APIs, you could check out the documentation here, and we are also actively reaching out to people to test the state API semantics and to gather feedbacks for potential improvement in the usage. All right, cool. So back to you, Sen, on the Ray 2.1 and 2.2 feature demo.
Okay. So let me actually go through the demo. So So the demo script that we're going to show today is just very simple Ray error example. So you're mixing up multiple different distributed workloads. For example, you're going to read images, and the read image is going to be loaded into the object store, and you're going to pre-process them using the Ray dataset API, and you're going to train using Ray train API, and all of them uses the Ray error, which is basically help you to connect them together. This is more detail of the low level operation here. So you're going to read from the S3 storage, and then you're going to read the data, split them, and run the pre-processing in 100 of workers. And you're going to send the data into 16 different train worker, send like a batch of data, and then they're going to train the models concurrently. And all of the actors are going to be all of the workload. This job is going to be managed by an actor called job supervisor, which is it's like technically implementation detail. Well, we're gonna see this actor from our demo, so I just added here. This is the actual script. As you can see, this is a pretty simple error workload. So you just have a data URL to S3 here. And you are going to have about 100 gigabyte of data. And then you're going to read images using the Ray dataset API. And then we are going to run the preprocessor. Basically, using the batch mapper, we're gonna apply this process image with label function, and then we're gonna create a trainer that has num workers, number of workers. And in this case, we're gonna have 16 of workers because each of worker is going to use GPU, and we're gonna use the cluster with 16 GPUs. So this is the actual cluster. Just in case people don't know, this is the Anyscale the managed Ray service. So everything's already configured here. So for the convenience, we're gonna use this for demo. The first thing I'm gonna do is to actually run the script. So I'm gonna run the script with the 100 gigabyte of data size. So we're gonna read about 100 gigabyte. There's gonna be total 16 workers, and epochs for each worker is gonna be 30. And we're gonna use the Ray job submit API. It's not necessary technically because if you just run this, it can also execute it. But we are using it to demonstrate some of the features related to the job. So let's actually start. So I'm gonna run the script. And then I'm going to run the dashboard. So the first thing I'd like to introduce is the node page. So if anybody use Ray, maybe this is the most familiar view you have. So we by default have all the node view. So every node existing in the cluster. So as you can see, there are 4 different nodes, and we are showing more detailed information, like what's the actual IP, which helps you to like SSH into machines in the worst case. What's the state of the node, and what's the actual node ID. This also helps you to see more details just by clicking it. You can see more detailed information. And there's also action you can perform. So for worker, you're able to actually see the log that exists in the worker. And also a lot of hardware utilization, the snapshot of hardware utilization of each node. So as you can see, this uses like 25 gigabyte of memory. You see each of node has 4 GPU devices currently not utilized. I think because the training hasn't started yet. So since we already have log, let me just actually jump into it. So by clicking the log or going to the log page, you're able to actually see all the logs on each node. And you can navigate through the logs just by clicking the button. And you can also search whatever log you're interested. So for example, let's say this debug state.txt help you to see an internal state of each Raylet. And you can actually search it and see the log, and you can see what kind of task has been running within each node, or like some other internal metadata. So going back to the node, we also provide the information of each worker. So you can see actually what kind of worker, what kind of task processes are running per each node. And as you can see, there are 2 actors and there are many idle. I think this is because it's running a task, but it's like too short, so it's not updated. And it also provides the same sort of information, what's the GPU usage, memory usage, CPU usage, as well as more actions. So not just the log, but we also provide the stack trace and the flame graph, so you can which uses PySpy under the hood. So you can actually see the live stack trace of each of worker. You can see this worker is actually doing nothing, it's just idle, this actor. And also you can perform the flame graph, which basically run the CPU profiling by default for 5 seconds. I think there are some sort of issues right now. Let's actually try a different one. But this helps you to run CPU profiling by default for 5 seconds, but you can also control the duration and actually see the flame graph from the result. It's still loading, so let's actually come back a little later. The next page I'd like to introduce is the job page. So as you remember, we run the job, and all the job that you run is going to be available from the job page. So I already ran multiple workloads here. Like for example, I run one IPython shell or like this workload twice before. So you can see all of them actually failed, stopped, succeeded. And this is the currently running workload. As you can see, we are running the PyTorch training and run for 3 minutes. And then the new feature is you're also able to see the task breakdown. So you can see how many tasks are actually running for this job, how many has been finished, and that sort of information. And of course, you're also able to see the log. So in this case, you can see the log of the job, which is actually the same output as here. But I think the flame graph is returned. I guess flame graph, there's nothing happening. But you can also control the duration, and there's also native, which helps you to see the C++ or C stack trace. If you're using like library like TensorFlow, PyTorch, this can also be very useful when you actually CPU profile. And so for the job, by clicking the job ID, you can actually see even more details of your job. So along with this metadata, you can actually see what kind of task actually is running or has been running. So you can see you had a lot of map block split to split data. There are 500 of them, and right now you're actually running just one Ray train worker, and one is currently waiting for scheduling, and there is one train that's running. So the next feature I'd like to introduce is actor page. So this already exists before, but we made some slight improvement. So you're also able to perform actions like the workers, and we also added more useful information like what's the actual resource requirement, and why actors exactly, what's the exit detail of each actor. So for example, you can see this job supervisor actor, which is managing the Ray job. It basically is dead because it's called exit actor, which basically means it has the graceful exit. So the last feature I'd like to introduce is Ray metrics. So this is the feature we invested a lot of time on 2.1, Ray 2.0 and Ray 2.2. So Ray has a native integration to Prometheus, and all the metrics are automatically exported to the Prometheus if you configure it. In open source Ray, you are supposed to set up Prometheus and Grafana. In any scale, this is managed service, so everything is already there by default. But when you actually set up, you should set it up Prometheus and Grafana running along with your Ray head node. And this has actually there's the Grafana backing behind, but every information also available in this metrics page. And in the future, we're gonna also have these graph actually spread out into like different tabs, so you can actually see them with other metadata. So let me actually go through some of metrics. So for example, you can actually see the task state, and you see there's 257 tasks that are running. I think this is the map block split. And then right now you can see there's only small number of tasks running. I think we are running the training right now. And we also have a breakdown by name, so you can actually see this Ray train worker that execute, which is running the train loop, basically is running. Similar in the same way, we also has this actor state. So you can see there are 17 actors currently running tasks, and there's one actor that's doing nothing. And you can also see breakdown by name. So I think the job supervisor probably actually maybe stats actor or the with parameter locals inner, maybe they're doing no job right now. That's why it's just alive and not running a task. Other than this logical information, we also shows the logical resource allocation. So if you use Ray, you specify num CPU, num GPUs whenever you start a task or actors, and when you are specifying them, you allocate the logical CPU. And the logical CPU and logical GPU, you're able to see they're actually running here. So when we are doing data processing, we run a lot of map block split, which uses one CPU. And right now you can see all of the workers are currently running and using one GPU. So you can see logical GPU allocation is like fully utilized. And there are other useful information like object store memory. It shows how many memories actually in shared memory, or how many memories in worker heap, how many memories has been spilled, and also placement group information. So all the ray train use placement group, so you can see there's one placement group available here. And of course, you can get the same sort of data through the state API as well. So if you do ray list placement group, you can see, sorry, my typo. You can actually see placement group is running, those placement groups running in this cluster. There are like one removed, one created. So I think this is the equivalent placement group as the one in this graph. And other than that, we also provide the hardware utilization. So you can see the logical CPU, but you can also see the physical CPU usage. And from here, you can actually see your CPU was not fully utilized. Maybe this means you can specify dumb CPU like 0.5 instead of 1. And in the same way, you can see the GPU utilization. And you can see GPU utilization is pretty accurate and it's fully utilized. And we also provide information like a disk usage, which helps you to see the like spilling related information. So if your data is really large and a lot of objects are spilled into disk, you can see if they're slow or fast from these metrics. And also the memory usage, which helps you to figure out whenever there's out of memory, you can see what node caused out of memory, and also what component caused out of memory. So in this case, you see most of memory is used by Ray workers. And also other nice information like GPU memory usage or the network, which is useful to figure out the data transfer between objects. And also, if you actually want to modify the graph or add more data, you're actually able to just jump to the Grafana and you can just build your own dashboard here as well. All the Ray metrics are available with the Ray as a namespace, and you can see not just the metrics that are available from the dashboard, but also other internal metrics that are available in Ray. Okay, and this is all about the demo today, and I'm gonna pass again to Ricky, and he's going to talk about the roadmap for 2.3, 2.4, and maybe the more feature versions of Ray.
Awesome, thanks, Dan. Yeah, so let's quickly go through what other things that we're planning to work on that we know for sure that we're gonna be working on. But also at the same time, we're gathering user feedbacks. So this kind of like a planned roadmap versus like a confirmative roadmap, or it's usually like a subset of the things that we're going to be doing. So the first thing that we definitely going to be doing is the state API beta. So currently state API is in alpha stage. So we will be working on adding more information as we heard from the users. So things like the metadata or historical states information, resource usage, exit code, or other cross different resources, like how many tasks are being run on a single actor, things like that. So we'll be adding all those information that are important to users of Ray. And then we will also be stabilizing the API, meaning that we will be fixing the return, the schema, and also maybe the input and options, so that people could actually feel comfortable and confident in using the state API to build their own observability tooling. And lastly, like formatting options, or just in general, usability improvements to the APIs. And another thing is, of course, the dashboard. So as you see from Sam's demo, the dashboard right now consists of multiple pages or tabs that kind of independent from each other. So what we're gonna do is we were gonna synthesize them into a more natural workflow for the users, right? So you would group things together in a reasonable way, so people could people don't have to like jump around between different pages. And we will also be doing like revamping of the UI so that it makes more sense for most of the usages. One particular things that we're gonna also be adding onto the dashboard, other than the usability improvement on high level, is the task drill down. So we will be adding things like the timeline timeline of the tasks that you could see, Similarly with all the tracing stuff, like what tasks you have been running at what certain time. So this kind of visualization that you could get from the dashboard, like out of the box. You could also drill down into a tree structure of the tasks. So if your task spun a couple of other tasks, you could see like what's the progress so far in your job as you branch out to the leave task. So more fancy visualization into like things like a DAG, etc., for people to actually track the progression. So other than the task, some other visualization that we plan to add are things like the object transfer between different nodes, and also like the different size buckets of different objects. So those are also useful high-level information for users who want to keep track of their object store usage. Yeah, so this is definitely not the end of or everything of the roadmap. We actively look for feedback from the users because the success of this observability project really depends on the users' input and feedbacks. So if you have not, please join the Slack channel and also let us know what you think that we should be working on. So this is the end of the talk. Yeah, we are happy to answer any questions.
Thank you, Ricky and Sanbin. I think this was really an amazing amount of information that we actually have unleashed after 2.0 and 2.1. The amount of data, the amount of information, the amount of way you can actually dice and slice and look at through different lenses of what's actually happening behind the scenes is quite illuminating. And any MLOps engineer who's actually working on distributed application would just love this amount of visibility into the things happening behind the scenes. So I think this is wonderful. And we want you to have a look at it and give us feedback, as Ricky mentioned. A couple of things, Ricky, that popped into my mind when you were actually going through the state API. I'm not sure if you had mentioned it or was it something that I just took it for granted. What's the best practice when people are executing the state API? Would you recommend they do it on the head node on the cluster, or would they do it on the laptop and have it connected to the head node? What do you recommend? What are the best practices?
Oh yeah, so I think I briefly mentioned it at the first use case where we provide flag where you could connect to a remote Ray cluster, just like how you do with, by providing a Ray cluster address or the auto address. Yeah, so either way, if you're on the head node, you have SSH access, that would be awesome. Just like running that, and Ray will result you to the right cluster before you. But if you are remote, like you're local on a laptop, but you have a Ray cluster running, if you have the correct like dashboard path forwarding stuff set up correctly, you should be able to query the remote cluster just like you're on the head node.
Okay, good. Thanks a lot. What is the frequency of how often these stats or data is actually collected from each and every worker node, and is there like a pull or push mechanism to where the dashboard is running? How does that work?
Right. So
go ahead.
Go ahead, Sam.
Oh no, it's okay. You can go ahead. Yeah.
Okay. Yeah. So for now, there is a mixture of push and pull model. So from the data sources contain things like the GCS or workers. So for different resources, for example, for task information, we currently pull from individual worker, and that's kind of query on demand. And for actor information, because this already centralized in the GCS, we just query the GCS. Then for objects, we also do kind of like distributed pulling from the individual worker. Yeah, so the underlying backend, for example, how the task information will be propagated to the users, we're actually working on that for optimizations. So I think in the future it will be more of like a pulling model where most of the information will be made available in GCS, and then the state API will query the GCS.
Oh, so the long-term plan is actually have a central repository with GCS where all the workers are just going to through gRPC storing in GCS, and then the dashboard just pulls everything from it on periodic basis. Correct?
Yeah, that's right.
Okay. Another question that popped into my mind. I'm a data scientist now. For example, I think this would be something either Philip or Frank might be interested in, how the operator is actually working in terms of the data. And if they wanted to collect this particular statistics in how long the operator is taking, or if they're collecting any other metrics that they want to show, how can they, how can they integrate with the Ray dashboard? Is there an API that they can actually use to export those metrics so that they can actually show the dashboard alongside with other stuff that we are showing? Is there a way people can extend it? Can you shed some light on that?
So for now, I think
Mhm.
we are not supporting any API like that. Like you can modify the Ray dashboard. So I think the best solution right now is to actually modify the Grafana and build your own dashboard and export it, and start the Grafana together with your own dashboard. But if this is something that many users want, we can also start looking at providing APIs and stuff like that. Yeah.
But if they store the data independent of metrics in the Grafana, can we actually also pull that from the Grafana and show it alongside our dashboard? Is that possible? Or they would have to have a different dashboard?
So right now the code is embedded, like we hard code, like what kind of what kind of graph we want to display. Yeah, so that's not possible now. Yeah.
Okay, great. I have a couple of questions from the audience. A good friend of mine, old good friend of mine, Chris. He's asking, what is the relationship, if any, between Ray placement groups and AWS EC2 placement groups? Are they different? Or one is an abstraction over the other?
They're completely different thing. I think we just happen to have the same name. So Ray placement group is the API to reserve the logical resources in Ray. So you're able to like, for example, like things like tune or train, you want to make sure all the like training actors are started at the same time. And then they are, when you run multiple trial, like tune trial 1 and 2, you don't want each trial to have like a partial allocation. So placement group is used to just make sure you have resources, like you reserve resources atomically in the cluster. I think AWS placement group is completely different. It's basically to decide where to place your EC2 instances, like, if I understand correctly.
Okay. So one is atomicity of reserving the resources guaranteed, and the other one is a preference of where you actually want something to be placed.
Yes, that's correct.
Okay. I hope Chris, that answers your question. But if not, we can ping offline. Rajiv asks another question about one of the challenges that they actually face when they click on the dashboard is through all the log files to find out if they have any error. Is there an easy way to grab all the logs, for example, lines with some error or some custom application UUID, or just have a single file with all the logs that they can actually grab easily? I think this is probably a common problem that people actually face when they have plethora of log files and they're looking for a certain pattern in the log file, how they actually go about doing that.
This is actually a good question. So I think, right now it's not possible. Like you do like through the dashboard. I think probably the best is you just download all the logs and grab it on your own from your terminal or something. And that's something how actually any skill solve this problem. This allows you to download the whole directory. I think within the dashboard, I agree this can be a nice feature. Something we are kind of not sure now is like, if I add all these features, it's like we're building another logging stack. Like, so yeah, I think it's something we should discuss further and need more user feedback. Yeah.
Yeah, so it's a good feature enhancement down the road if actually people actually need that. I think that the search capability that both you and Ricky provided is the glob that you can actually search the blog types, and then once you actually have the blog flight, maybe if the blog is small enough, you can just do a Control F and do a search string. But other than that, the specific thing that Rajiv is asking is a feature which could be desirable, which could be something that we'll definitely entertain. Another question the same person asked Rajiv is, would you have an option in the CLI command to show the logs between the start time and an end time. So they want an interval of some, some period, right? Right now, when we click on the log file, we actually see everything, from descending order to ascending order. Is there any way they can actually look at the interval? Does that make sense?
Yeah. Would you like to answer, Ricky? Or
Oh yeah,
this question?
sure. Yeah, I think this is kind of similar to like the searching capability. So yeah, I think Sam's concern that he raised just now, like we could make it really kind of like elaborate or adding more enhancement into it. But I think it's more like a trade-off. But I totally agree that these will be really useful features, and maybe we could pick it up on the roadmap going forward. And also, I feel like the search, the grab search capability is actually super important. I think that's personally how I did most of debugging, where like I want to search for keywords. Yeah, so maybe something that we will definitely consider for the logging capability.
So, I mean, should we ask Rajiv to go ahead and file an issue, and that way we all can actually keep track of that? Okay, I'll ask him. Rajiv, if you're online, please do file an issue. Say that this was presented at the webinar, and at the meetup, and it would be nice to actually have that, and we'll definitely prioritize that as we are planning our roadmap ahead.
Absolutely, yeah. That would be great.
Okay, he said I'll file an issue. Thank you very much. Thanks. That'll be a good Christmas gift for us. Any other questions? Let me see. I don't see anything, but my goodness, I mean, I'm quite impressed. And this is not to ingratiate myself or to evangelize it, but these are the lenses that people actually look for. The granularity of the amount of data and what this particular task is doing and what this actor is doing and where it is in its stage in the grand scheme of things, especially the granularity in which. Especially when you're doing the training and you have GPUs and you have CPUs and you actually find out where things are, just quite amazing. And I do like the idea of how the second level of the roadmap where we are giving a hierarchical view so people can actually go down. Right now, we have data all over the place, which is fine, but it's nice to actually have the hierarchical view that Ricky was talking about, where you can see the what they call the CLI, the executive summary of what things happening in the world, and then you can drill down into things. That's great. I don't see any other questions coming up, but I do want to thank Philip and I do want to thank Frank for both of you taking time and sharing with the Ray community how you guys are actually using Ray, especially in the spaces that you are dealing with large vector spaces, and how Ray is doing. And Philip, I really encourage if you just file some issues that you actually ran into. We definitely want to look into that, because anything that we can actually help to unblock you to use Ray at the scale that you're actually using, we definitely more than happy to do that. So please do file those issues. And thanks a lot, Ricky and Sangbin. I know you're up in across the Pacific Ocean early in the morning, but thanks a lot for waking up and doing this meetup. So thanks a lot for you guys, and don't forget Ray Saturday is coming up. Keep your eyes open for the CFP, and we'll share these slides and we'll share the video with the meetup. So thanks a lot. All right, cheers.
Thanks. Have a good one.